Hello and welcome to the Abingdon Physics YouTube channel. Today we're going to be doing Edexcel IGCSE topic 3 waves, and in particular the light section. I'm Mr. Willoughby and I'm going to be guiding you through it. So the spec points we are covering today will be 3.14 to 3.22, with the main focuses being on reflection, refraction and total internal reflection. You can pause now if you want to have a read through these, but we're going to go through them. So up first we have spec point 3.14, 3.15 and 3.16, and the first point is to know that light waves are transverse and they can be reflected or refracted. And when we say a transverse wave, we know that light oscillates perpendicular to the direction of energy transfer. And we've got to remember that we're using the word oscillates and perpendicular in our answer. We need to also know how to use the law of reflection. So our diagram for what the law of reflection looks like should be something like this. In black we have the plane mirror, and in blue and dashed we have the normal line. The normal line should be at 90 degrees to the surface of the mirror. The incident ray is hitting the mirror, and that is where our light is coming from. So maybe the incident ray is from the object that we are about to see, and the reflected ray is in green. Whenever we are measuring angles on a ray diagram, it is really important the angle we are measuring is between the normal and the ray. So our angle of incidence, which I'm drawing on now, is between the normal and the incident ray, and it is given by the symbol I. And the angle of reflection is between the reflected ray and the normal, and it is given by the symbol R. We then must know the law of reflection, which is that I is equal to R. Now we have refraction. Refraction is the bending of light as it enters a different medium due to the light's changing speed. So different mediums, light travels different speeds in. Light is fastest in air, and then as we change medium, it starts to travel slower. So in glass, it travels slower, and in diamond, it travels really slow. And it is these changes in speed that causes the light to change direction. So here is an example of a ray diagram for refraction, where light is going from an air to glass, so from a less dense to a more dense medium. As the light goes from the air to the glass, the ray slows down and bends towards the normal. And we can once again label our angle of incidence between the normal and the incident ray, and we can label our angle of refraction between the refracted ray and the normal. Unhelpfully, the symbol R is used for both refracted rays and reflected rays. Now moving on to spec point 3.17, a practical to investigate the refraction of light using rectangular blocks, semicircular blocks and triangular prisms. There isn't really much to say about this. There is another practical that we're going to talk about in a moment that is the main practical of this topic, but it's to understand that when light goes into a glass block, it can refract, and when light is exiting a glass block, it can totally internally reflect or refract depending on what the angle of incidence is. So spec point 3.19 and 3.18 are about investigating the refractive index of glass using a glass block, and to know that n equals sine I over sine R. So let's talk about the experiment needed to find the refractive index of a glass block. To start with, we will place a glass block on a piece of paper and draw around it. Once we have drawn around the glass block, we will shine a ray box through the glass block at an angle. Now obviously we can't draw the refracted ray straight away as it is behind the glass block. So what we will need to do is we will use crosses to denote where the light is entering and where the light is emerging from the glass block. These will be our incident ray on the glass block and our emergent ray from the glass block. We can now turn off the ray box and remove the glass block which we have drawn around previously. We can now draw over where the crosses overlap. So in red I've drawn the incident ray, and in blue I've drawn the emergent ray. These are going to touch the glass block, and from where they touch the block we can connect them up, and in green I have drawn the refracted ray connecting these two together. From here I can draw my normal onto the glass block where the incident ray meets the refracted ray, and I can measure my angle of incidence and my angle of refraction, and I can put them into a table. I'm now going to repeat this process multiple times, obtaining multiple angles of incidence and angles of refraction. Then I'm going to add more columns to my table for sine I and sine R. With the values of sine I and sine R calculated, I will plot a graph with sine I on the y-axis and sine R on the x-axis. After plotting my results, I should see that I get a straight line of best fit, and the gradient of this line will be equal to the refractive index of the glass, where we should know that the larger the refractive index, the more the light is going to bend and the slower the light will go into this new medium. So refractive indexes that we should be aware of are water, which is about 1.3, glass, which is about 1.5, and diamond, which is about 2.4-ish. So now we move on to spec point 3.21 and 3.22, where we are talking about the critical angle C. And the way that I find best to describe this is by drawing 3 different glass blocks, which are all semicircular. So on these 3 drawings, I have drawn normals and rays of incidence with varying angles of incidence. The critical angle is the angle of incidence for which the angle of refraction equals 90 degrees. This will only ever occur when going from a more dense to a less dense medium. That's because when we're going from more dense to less dense, the ray is going to speed up and move away from the normal. So if I draw my ray of refraction onto the first one, I will see the light exiting the glass block and bending away from the normal. So because my angle of refraction is less than 90 degrees, I know that my angle of incidence is less than the critical angle. For my second glass block, I'm going to have the angle of incidence equal to the critical angle. Therefore, the ray of refraction is perfectly along the glass block at 90 degrees. And now finally, we have when the angle of incidence is greater than the critical angle, no refraction is going to happen, and we get total internal reflection occurring, where our angle of reflection will be equal to our angle of incidence. So the key takeaway of this is that when the angle of incidence is less than the critical angle, we get refraction out of the glass block. When the angle of incidence is equal to the critical angle, we get refraction at 90 degrees. And when the angle of incidence is greater than the critical angle, total internal reflection occurs. And then we have this equation, sine C equals 1 over n. And I can rearrange this for n equals sine inverse of 1 over c. This means the greater the value of n, the smaller the critical angle. Therefore, the larger the refractive index, the more likely light is to get trapped inside. And this is why something like diamond with a high refractive index of about 2.4 is really sparkly, is because there is light trapped inside of it because there's loads of total internal reflection occurring. And our final spec point is 3.20 to describe the role of total internal reflection in transmitting information along optical fibres and in prisms. Now below I have drawn a rough sketch of what light going through an optical fibre looks like. So an optical fibre has an outside cladding and a glass core. The light goes through and inside the glass core, and it totally internally reflects at the boundaries so that the light can transfer really, really fast at the speed of light, 3 times 10 to the 8 meters per second, through the core. This allows us to transfer information really, really fast at the speed of light. And it's why fibre optic broadband about 10 years or so ago became a really, really big thing. So one use for total internal reflection could be for fibre optic cables for communication. Another use could be for endoscopes in medicine. And another use of total internal reflection could also be for periscopes for seeing. And with that, we can now get on to some questions. So question 1, we have a simple joining up the dots exercise. So total internal reflection will be this second one here. As we can see, it's reflecting inside the block. Refraction will be this bottom one, as we have a bending between 2 different mediums. And reflection will be our top one here. Next, we're asked to state 2 properties that all waves have in common. There are in fact loads of answers we could give here, but the easiest ones to give are probably that they can transfer information and energy without transferring matter. They all have a wavelength, they all have a wave speed, and they all have a frequency. So in this question, we are asked to describe an experiment to determine the refractive index of a glass block, and my answer should include a labelled diagram, the apparatus needed, and the method used. Now this is a 6-mark answer, and we can probably get 5 just from the diagram alone. So I'm going to draw the diagram. Now my diagram is drawn, I can start giving my explanation, which will involve shining the ray box through the glass block and making sure that we have drawn around the glass block as well. We will then record where the incident ray has gone into the glass block and where the emergent ray has gone out of the glass block using crosses. We can then join those to the glass block, and we can draw our normal on, and we can then connect the emergent ray and the incident ray using a straight line from each side of the glass block. From here, making sure we use a protractor, because we are stating all the equipment that we use in every single experiment method. So using a protractor, we measure the angle of incidence and the angle of refraction. Once we have an angle of incidence and an angle of refraction, we are going to repeat this process multiple times to obtain multiple different angles of incidence and refraction. And then we are also going to find sine angle of incidence and sine of the angle of refraction. And then we can plot those onto a graph of sine I against sine R, where the gradient will give us the refractive index. So now let's check our answer against the mark scheme, where we can see that we need a method for creating a thin beam of light, and we have to mention that we are going to use a protractor. So that is our ray box and our protractor getting our first 2 marks. Then the method will be to draw around the glass block, shine light into the block at an angle to the normal, mark the incident and refracted rays, measure the angles from the normal, and then repeat for different angles of incidences. And once we have the different angles of incidences, we need to say that we are going to graph sine I against sine R, with the refractive index being found from the gradient. And now we see a question with a similar setup to the experiment that we just had, and it wants us to add onto this diagram where some of the light is being reflected at point A. So what we need to draw is we need to draw our normal at point A, and then we need to add our I here, and then our angle of reflection is going to be equal to our angle of incidence due to the law of reflection, and the marker is going to judge that by eye. So if you have a protractor, amazing, I would advise using a protractor. If not, as long as you're close, the marker should be giving you that mark. And now we go on to II, where you 100% need a protractor, because we are being asked to determine the angle of incidence and the angle of refraction of the red light at point A. So once again, I need to draw my normal, and I can label this I, and I can label this R. We need to remember, and this was so important, that the angle of incidence, or any angle that we take, is always between the normal and the ray. The angle that we are measuring is always between the normal and the ray. And so you would use a protractor now to measure the angle at A. A quick sense check we can have on this question as well is that the angle of incidence is going to be greater than the angle of refraction, because we are going from a less dense to a more dense medium, so we're expecting light to bend towards the normal. So if you're getting an angle of refraction greater than the angle of incidence, you know you've done something slightly wrong. So next, we're asked to use our angle of incidence and our angle of refraction from the question before in order to find the formula for refractive index and then calculate the refractive index for the red light. So we should know that N equals sine I over sine R, and then calculate the refractive index of glass for red light. Remember, we're always going to write out the equation sum answer unit. So N equals sine I over sine R being our equation part. Then our sum is sine 60 over sine 31. And this gives us an answer of 1.68. And this seems somewhat reasonable for glass, As glass, we're normally looking around 1.5, maybe 1.4, maybe all the way up to 1.7. We're now given a situation where we have blue light going through the same glass block instead of red light. So before we had red light, and red light is the dashed line that is shown here. Now, different lights have different refractive indexes. So blue light has a higher refractive index. That means it is going to bend more towards the normal. So if I'm drawing my blue light on, it will look something like so. It's going to bend towards the normal more. And then when it exits the glass block, it's going to be parallel with the previous red light ray. And that's because when they're back in air, they're going to travel at the same speed, so return to the same angle. We now move on to a question about critical angle, and we have a transparent material here, and there's points X, Y, and Z, and then where it leaves. So the transparent material has a refractive index of about 1.7. State the formula linking refractive index and critical angle, and we have n equals 1 over sine C. Okay. Calculate the critical angle for the transparent material. Well, we can rearrange this to be C equals sine inverse 1 over n, which is equal to sine inverse 1 over 1.7, and this gives us an angle of 32 degrees. And we remember to show our equation, sum, answer, and unit. So next we're asked about what is happening at points Y and Z. And this is where we have total internal reflection. And we get total internal reflection because the angle of incidence is greater than the critical angle, and because we are going from a more dense to a less dense material. This is because we are in glass, the more dense material, and would be going into air. And if we check this against the mark scheme, we see 1 mark for total internal reflection, 1 mark for angle of incidence is greater than the critical angle, and 1 mark for light would be going from a more optically dense medium to a less optically dense medium. And finally, we're asked to give 2 uses of total internal reflection. One, we could say optical fibers, either for endoscopes or optical fibers for communications. And another example of a use is a periscope. And if we check that against our mark scheme, we see optical fibers and another prismatic use, so periscope, binoculars, or something similar. So thank you for watching this video on Edexcel IGCSE Topic 3 Waves and the light section. I hope this was useful. If you have any questions, leave them in the comments, and make sure you do past paper questions, as these are the best way to revise. Right, thank you for watching. Remember to like and subscribe.